Lorentz transformations relates the space and time coordinates of an event as measured into inertial frames. In the standard configuration, S prime moves at constant velocity v along x, positive x relative to s. So we have the standard configuration here. This is the S prime, and we have the S prime here, and we have the S prime, so y prime and x prime here, and the origin here is O prime. So S prime moves to the right with velocity v relative to s. At t equal to t prime equal to 0, origins coincide, so O is equal to O prime. So we have the Lorentz transformation equations, x prime here. So from s to s prime, so we have these equations. From s prime to s, so we have these equations. So where the gamma here is equal to 1 over 1 over the square root of 1 minus b squared over c squared. C here is the speed of light here. This is constant. So for v less than c. So key ideas, Lorentz transformation embodies the two postulates of special relativity. The laws of physics are the same in all inertial frames. So the speed of light in vacuum is the same constant c in all inertial frames. So when c is much less than c, the gamma here, which is the Lorentz factor, so the gamma here approximately 1 plus 1 half b squared over c squared. So this is the expansion for this factor. Reduce it and the Lorentz transformation reduces to the classical Galilean transformations. So here are the three sample problems utilizing the Lorentz transformation equations, complete with the step-by-step solutions. So we have the problem 1, problem 2, and problem number 3 here. So for problem number 1, finding moving frame coordinates here. So an observer in a stationary frame S records an event at position x equal to 5 times 10 to the 8 meter here. And at time t equal to 2.0 seconds. So rocket frame is prime, moves along the shared positive x-axis at a constant speed of 0.6 of the speed of light here. So find the position x prime and t prime of this event as measured by the rocket observer. Use c equal to 3 times 10 to the 8. So calculate the Lorentz factor here. So first calculate the dimensionless scaling factor gamma using the relative velocity v equal to 0.6 c. So we have this by substitution. So the Lorentz factor is equal to 1.25. There is no unit for this. So transform the spatial coordinates. Apply the spatial Lorentz transformation formula to solve for x prime. This one. So by substitution here, so x prime here is equal to 1.75 times 10 to the 8 meter here. So transform the temporal coordinates. Apply the temporal Lorentz transformation formula to solve for t prime. So here's the formula. So we substitute the formula here. 1.25 for the Lorentz factor. And we have the time here is 2.0 seconds. So the velocity here is the speed of light is 0.6. The given speed here is 0.6 of the speed of light, and x here is 5 times 10 to the 8 meter over c squared. So by substitution, we have the t prime equal to 1.25 seconds. So relativistic simultaneity. For example, here two light bulbs flash simultaneously at t1 equal to t sub 2 equal to 0 in reference from frame S. Bulb 1 is located at the origin x1 equal to 0 and bulb 2 is located at x2 equal to 8 times 10 to the 8 meter. Frame S prime travels fast along the positive x-axis at v equal to 0.6 of the speed of light. So find the time interval delta t prime equal to t prime 2 minus t prime 1. Find the time interval between the two flashes according to an observer in frame S prime. So determine the Lorentz factor here. So the Lorentz factor is given 1.25. Formulate the difference here. So find the coordinate differences in terms of the Lorentz transformation rules. So delta t prime equal to t prime 2 minus t prime 1. So this is equal to the given formula, the Lorentz factor times t sub 2. So this is equal to t prime here, t prime 2. And this one is equal to t prime 1 here. So if we simplify them, this is equal to the Lorentz factor times delta t minus v delta x over t squared. So evaluate the time interval here. Substitute the value of delta t equal to 0 and delta x equal to 8 times 10 to the 8 times to the 8. So into the delta equation here. So the delta t prime here is by substitution here is equal to negative 2.0 second. So the negative sign here means that in frame S prime, the flash at x sub 2 happens at 2.0 second before the flash at x sub 1. Finding a stationary frame coordinates, we have the problem 3 here. An observer inside a moving spaceship frame S prime, v equal to 0.6 of the speed of light relative to S, records localized explosion at the position x prime equal to 4 times 10 to the 8 meter and time t prime equal to 2.0 s. Find the position x and time of this event recorded by the stationary observer on the space station and premise. So set up the inverse formula here. So to transform from the moving S prime back to the stationary frame is use the inverse Lorentz transformation, which flip the signs of the velocity term. So we have x here times the Lorentz factor times the sum of x prime and vt prime. So time here is equal to Lorentz factor times t prime plus bx prime over c squared. So these are the formula. So we are going to stop it here. Calculate the stationary position here. So our Lorentz factor here was 0.25 and x prime here is equal to 4 times 10 to the 8 meter plus v here. So v here is equal to 0.6 of the velocity of light times t prime here is equal to 2.0 seconds. So x here is equal to 9.5 times 10 to the 8 meter. So calculate the stationary time. Substitute the given values into the inverse time transformations. So this is time here. So by using this formula, this one. So by substitution, the given here, so 1.25 here. So this is the formula that we are going to use. Okay, so this is we have the t here. So this equation, we use this equation and we substitute the given in the equation. So we have this t equal to 1.25 times 2.8 second equal to 3.5 second. So final calculation summary. For problem 1, the coordinates measured in frame S prime are x prime equal to 1.75 times 10 to the 8 meter. And t prime here is equal to 1.25 second. So for problem 2, the time separation between the two flashes in frame S prime is negative 2.0 second. For problem 3, the coordinates measured in S are 9.5 times 10 to the 8 meter. And the time here is equal to 3.5 seconds.